Hello, my name is Carol and I'm a professional practice coach at the Institute of Physics. In this video, two of my colleagues and I will run through the models that we find particularly helpful for teaching students about circuits. We'll focus on how they can address misconceptions and also think about the limitations of each model. Models can be particularly useful in physics because they can turn what is a very abstract idea into something more concrete and tangible. So some of the models that we will look at are physical. Some of them are moving into a more pictorial way of representing something, and then finally you'll see how that then translates to a more abstract representation. We'll start with Dan, then move on to Nilofer, and I'll wrap up. Enjoy.
Hi, my name's Dan, and this is a short video to explain a model for understanding how electrical current goes through a piece of wire, just like this one. What you're going to need for this is some marbles, some 100-gram masses on hangers, some little bits of scrap cardboard, some blue tack, and one of these, which is a Dynamics trolley track. I'm going to arrange my masses into a regular pattern. So obviously it's just a model and a simulation, but each one of these masses is going to represent an ion in the lattice. And then what I'm also going to do is I'm going to, in between these ions, put marbles. Now each marble here is going to represent an electron that is free to move. You might say it's one of the sea of delocalized electrons that exists in a metallic lattice. Now these marbles are potentially going to drift to one side of the track and get stuck down the edge of the track. So to prevent that, what you can do is get some of these bits of cardboard and some blue tack, and I'm going to blue tack it to the side of the track like this, so that the fold out bit's sticking out. And what that's going to do is any marble that comes across here, as it rolls down, it's going to be forced back into the middle. I'm now going to simulate and model an electrical current flowing through this wire. So what I need to do in order for that to happen is I need to make all of the marbles move in the same direction at the same time. I'm going to lift up the far end of the track, and then each and every marble along the whole length will start moving by the force of gravity down the track toward the tray. So here goes. So just a gentle lift, not too steep. So in this model, when we lift up the track at one side, we apply a potential difference across the wire. So there's an energy store. But what happens to it? Well, the marbles collide with the masses. And as they collide, they cause the mass to move just a little bit more than they were doing before. So that's exactly like what happens in a wire when a current flows. Collisions between electrons and ions cause the ions in the lattice to vibrate a bit more. And this results in a heating effect that we perceive when a current flows through a wire. So this model really helps to link those ideas of chemical structure of a wire with some of these ideas of energy. If we're thinking about potential difference and currents, we can measure those directly, because the potential difference in this model is very similar to measuring the height that we lift the track. And the current is very similar to the rate of flow of marbles. So we could time, for example, how long it takes for all the marbles to come off the end of the track. Electrical resistance in this model becomes due to the collision of an electron with an ion in the lattice. And the more collisions there are, the higher the resistance. So in terms of strengths and limitations, obviously the marbles are all present everywhere in the wire when you start this model. And that's good, because that shows, just like in a real wire, there are electrons everywhere. But unfortunately, in this model, the electrons sort of empty out of the wire as the model goes on. So you'd probably need to think about that in terms of Are we communicating to students that electrons kind of empty out of wires as the current flows? Well, I don't think so. That's a limitation really of this model. We'd need some kind of conveyor belt system or something to keep them going round and round to address that. But pointing out the limitations is actually a really useful thing to do. Now over to Nilufer, who will share two models to help us address some misconceptions with circuits.
Hello, I'm Nilufer Wijitungi and I am an education coach at the Institute of Physics and also a practicing physics teacher. At primary school, students learn about simple circuit components such as bulbs, lamps and switches. They will also learn how to build these into simple circuits. However, when they start secondary school, they will have very little knowledge or almost no knowledge about what a current is and how fast it is in a circuit. Here are two activities which address their understanding of what a current is and how fast it moves in a circuit. So what we have are two circuits, one large loop on the right hand side and one a smaller loop on the left hand side. Both circuits will have similar batteries, bulbs, switches. However, on the left hand side you may use only a couple of wires to make the circuit, and on the right hand side we're going to be using many more wires. So for example, you may ask your students to each connect a wire to build the very large loop that we see there on the right hand side. Now then you pose the question to the students, which one of the bulbs glows first when the switches are simultaneously closed? Now you may gather their thoughts using mini whiteboards, for example, and what you will typically find is that students will opt for the smaller loop having its bulb come on first. So then you can either turn the switches on yourself or you could get a volunteer to come and do so, and when that is done, what everyone will observe is that actually the bulbs glow exactly at the same time, okay, or instantaneously. So a really good follow-up question to this is, how fast is the current? Okay, so again, you could gather students' thoughts up using mini whiteboards, and typically they will opt for the current moves very fast because they would have experienced in this example, as that's actually when you close the switch, the lamps come on immediately. However, this isn't the case, and here is quite an effective model to address this misunderstanding. Okay, so if we have a very long tube of toothpaste with the lid off, so there's a photograph here of a typical example, and you squeeze the bottom of the toothpaste, okay, what you will see is that the toothpaste comes out instantaneously at the top. Now, how does this model what's happening in the electric circuits? Well, just like the push at the bottom of the toothpaste, the battery pushes the charges which are already there inside the wires and inside the filament of those bulbs, okay? So they all move together at once the moment that battery pushes on the charges, on the free charges which are existing in the circuits. Now, likewise, the toothpaste has the paste already sitting there, and therefore when you give it a little squeeze, every single bit of the paste moves instantly, right? So another effective model here is that the actual speed of the current, okay, is demonstrated by how fast we see the toothpaste coming out the top of the toothpaste tube. So if we focus on the top of the toothpaste tube, and you can actually see the paste is creeping out ever so slowly, even though the immediate effect is for it to come out when you've given it a little push at the bottom. And this models the way in which current moves in the circuits. So they are actually, the charges that make up the current are actually moving along typically about a couple of millimeters every second or so, and they're creeping along through the wires just like that toothpaste is creeping through the toothpaste tube. The rope loop model is a classic way to demonstrate electric circuits in a classroom. This model demonstrates several key ideas as well as addressing some common misconceptions. So what you will need is some rope, something around 3 meters or so will do, and preferably nylon rope, which you can then melt the ends of and attach together like so. Then you can also use some tape like this, just to smooth over that attachment there. Now, preferably if you have rope that is speckled all the way through, that would reinforce the demonstration a lot better. If not, you can actually put dots along the rope like so, and this will just allow students to see how the rope is moving through their hands as you carry out the demonstration. Here we have a mechanical analogue of an electric circuit. For example, the teacher models a battery and the students model components such as bulbs. It's best to just use 1 or 2 volunteers, as too many hands can lead to gripping the rope too tightly or pulling too hard, which will make it difficult to make the rope move. Also, do take care that students don't grip too tightly and burn their hands. To model the battery providing the voltage, make the rope circulate, pulling it at a steady rate. The rate of flow of the rope is the current. To model one bulb in the circuit, a student volunteer grips the rope lightly with one hand so that the rope can slip through easily. The rate of flow of the rope is observed to be the same at the battery and at the bulb. Here, a second hand is used to represent 2 bulbs in series. Again, the rope is gripped lightly by each hand. Now, as the battery makes the rope circulate, the rate of flow of the rope will decrease compared to when there was only 1 bulb. In a circuit, this represents a lowered current due to an increase in resistance. So some key questions to ask students when you are carrying out this activity. Firstly, where did the current start flowing first? How does the current in and out of the bulbs or battery compare? What is happening to the light bulb's hand? Now finally, I'm going to just go through some comparisons of the model with the circuit. Firstly, the rate of flow of the rope into and out of the teacher's and those of the volunteers' hands is the same. Just like with the circuit, the rate of flow of current into and out of the battery and bulb are the same. Secondly, on the rope model, we have dots that already stay there on the rope. They start moving at once and at the same speed everywhere around the loop. Similarly, for the circuit, we have the free electrons which are already there in the circuit, and they start moving at once and at the same speed everywhere around the circuit. Another comparison is that as the rope moves, the temperature of the volunteer's hand will increase and raise the temperature of the surroundings. Also, the energy stored chemically by the battery has decreased, and the thermal energy store of the surroundings has increased. In a similar way for the circuit, as the current flows, the temperature of the bulb's filament will increase and it will raise the temperature of the surroundings. The energy stored chemically by the battery has now decreased and the thermal energy store of the surroundings would have increased. And a final comparison is that with the model, energy is being transferred by the whole system working mechanically. There is no way that one side is carrying energy from the battery to the volunteer's hands. Likewise, for the circuit, energy is being transferred by the whole system working electrically. There is no way that the electrons in the wires are carrying energy from the battery to the bulb. So the rope loop model is a very useful model, but like all models, it does have its limitations. So now I'm going to hand you over to Carol, who's going to share with you a final model which will help students understand the link between their observations of circuits in the classroom and what the charges are doing inside the wires.
As mentioned in the introduction, one of the things we have to do as physics teachers is explain very abstract ideas. One thing that can help with this is to start with a concrete example or representation before moving on to a visual way of showing something and then building the abstract idea on top of that. So taking a concrete, then pictorial, then abstract approach to teaching. The model that I'm about to share, which is a PhET Colorado simulation, is able to show different ways of representing circuits. It's a resource that is freely available for schools. Students can download them onto their own devices, and there are lots of teaching resources and ideas of ways to use them on the website. So please do take a look at the other simulations as well.
So for circuits, the symbols and the circuit drawings are a very abstract version of what's on students' desk. So it's helpful to start with a very concrete version of that. I find the PhET Colorado interactive simulations brilliant for this. If you look at their circuit construction kit simulation, you can see that you can have components that look like components that we use. You can see the charges, you can also look at conventional current movement, and you can also remove the charges if you want. But I find it quite helpful to have the charges in there, because when you close a switch, you can see they all move together. You can see that they're already in the components, already in the wires before you connect up the circuit and have your complete loop. So that's really great for addressing several misconceptions about circuits. You can also make comparisons on your screen. So here I've changed the number of cells, and I can compare the brightness of the bulbs and the speed of the charges. So we're really trying to make visual and make explicit to children how the macroscopic observations that they make link to the microscopic and submicroscopic explanations of the moving charges inside the wires. We can also change the number of bulbs with a constant number of cells, and again you can see the speed of the charges and the brightness. This is so great for getting across these ideas so that students have an understanding of what's going on before we start teaching the maths, before we start introducing the symbols. What we can also do is have voltmeters, so we can see that these need to be attached across a component to measure the voltage across it. We can also add ammeters to our circuit, which have to be added in series, and we can measure the current at different parts of the circuit. So this is absolutely brilliant for showing to students things that sometimes would be a bit tricky to demonstrate on a lab bench with real equipment. You can also talk about parallel circuits in a way that again makes clear to students that there are different ways of setting them up that are all equivalent. So these all look like quite different circuits, but actually you'll see that each one has got a loop with one bulb connected to a cell, and then a second loop with a bulb connected to the cell. Similarly, you've got a loop there and a loop there. You've got a loop there and a loop there. Now this last one is what your conventional drawings of a parallel circuit would look like. But actually a lot of students won't build one like that. They won't have this many wires. And so it's important to explicitly explain there are different ways of setting it up, and you can then compare this to photos or under a visualizer what you've got on your lab bench. Again, you can then start building towards showing them what they would look like with the symbols drawn instead, and why we draw them this neat way rather than looking like a tangled mess of wires. One thing that is a limitation of this model is it looks like there are only a handful of charges in your circuit, which is obviously not accurate. The way they travel smoothly in a smooth path is also not accurate. So again, it's important to think about a range of models that all show slightly different things, but also have different limitations as well.
As we hope we've made clear in this video, these models are very powerful tools for helping students to understand what is going on in the wires and components of a circuit that helps us to then explain the observations we make in the classroom. The models can also be used to address common misconceptions. For instance, many students mistakenly think that the charges are all coming from inside the cell or battery, and using these models can help show them why this is really obviously not the case. We hope you find these models useful for your practice. Please do watch the other domains videos on this topic and also other physics topics. And do join in with our live sessions, which will all be advertised on Talk Physics.